The next topic we have to address is out of chapter 9, center of gravity, center of mass, and centroid. So these are three very closely related topics. Again, it's all about trying to determine where we can replace rigid body with a single point force or point volume. So we're going to go ahead and talk about what these are to begin with. Centroid is the easiest one. It's just the geometric center of the object or the rigid body. Okay, dealing with any sort of object here, we can find the geometric center, be it a circle, rectangle, whatever odd shape we have as well. Okay, a center of mass, okay, is the same idea. But essentially we have to take the center and kind of weight it by mass. So if we have something that's denser on one side than the other, okay, it's the point at which mass is evenly distributed in the rigid body. Okay, so if I have a simple beam here, the centroid is going to be right in the center of my beam. Okay, if, however, this thing were, for whatever reason, denser on the right-hand side than it is on the left, the centroid would still stay right in the center. The center of mass, however, would shift over towards the denser side of things to make sure that there's an equal amount of mass on this side as on this side, as well as above and below. So no matter what line I draw through this point, I'm going to have an equal amount of mass on either side of it. And that gets weighted by the distance as well. We'll talk a little bit about that. It ties into moments. A good way to think about this is if you go back and think about distributed loads. Okay, we took our distributed loads and we'd simplify them down to a single point force. Okay, this is what we're doing here. If the mass is evenly distributed, the single point force, again, the single point of concentration of mass, will be right in the middle. If it's not evenly distributed, you have you end up using a moment relationship to find out where we can treat that mass as being concentrated. Center of gravity is the same idea, only now we're including gravity. Okay, center of gravity is use a little bit of a simpler definition here. The point at which we can apply a point force to replace the weight of the rigid body. Okay. So these things are closely related, and in most cases they're actually exactly the same. So we'll talk about kind of how that goes. All right, so going back to center of gravity here, that's exactly analogous to finding the center of a distributed load or replacing a distributed load with point force. Weight of an object is essentially its distributed load caused by gravity, and weight pushing down everywhere. We replace that by a single point force, and you'll see similarities when we calculate that as well. Okay, so the centroid can equal the center of mass, i.e. they're going to be in the same point, And this is conditional if density is uniform. Okay. If the object is the same density throughout, then its centroid, center of mass will be its centroid. Okay. And center of mass will equal the center of gravity, i.e. they'll be in the same spot. And this assumes if gravitational field is constant, i.e. the acceleration due to g, the acceleration due to gravity, g, is constant. Okay? So if we have a material that's uniform density, its center of mass is going to be at its centroid. Okay? If we're dealing with uniform gravity, which near the surface of the Earth we generally are, okay, this really only comes to play if you're changing altitude significantly enough that your gravitation is going to change. And so assuming gravitation is going to remain the same, then your center of gravity is going to be at your center of mass. Okay? So these are, for our purposes, going to be the same in almost every case. Later on in the program, you may get to the point where you deal with non-uniform densities. When you start dealing with non-uniform gravitational fields, that gets a little further along. That's pretty specialized applications there when you're talking about things happening in orbit and whatnot. So that's kind of what these are. The next question is, how do we calculate them? Where they are for these objects. Okay. If we take the simplest case, I'll do it in 3 dimensions, so it's not quite the simplest case, but if I have x, y, and z, okay, I'm going to have 3 particles in space here. Okay? Each of these little particles is going to have a weight. Okay? Easy enough. Okay, this is a system of 3 particles. Okay, the resultant weight is simply the sum of the 3 individual weights is W1 plus W2 plus W3. So again, here we're finding we're dealing with weight, so it's going to be finding the center of gravity. Okay, for our system of 3 particles. Okay, I'm not going to have numbers in here. This is kind of just more of an example. I want to deal with this in terms of the symbols and in terms of the relationships. Okay, so we find the total weight. And now we're going to try and find the point in x, y, and z where we can replace these 3 weight vectors by a single weight vector. Okay? The idea here is if we find that point, not only will the total force applied at that point be equal to the total force of those 3 individual forces, but the total moment generated by around each of the 3 axes by that individual force will be the same as the total moment generated by these 3 forces around all 3 axes. So essentially we have that the summation of moment for each of these has to equal the total moment for the resultant force as well here. So we end up doing this very similar to what we had when we did distributed loads here. So we have summation of moments, say about the x-axis to start. Okay. Summation of moments for these is going to equal, well, we have W1 times its distance from the x-axis is y. Yeah, we're going to have the x position, center of mass. Okay, so plus W2y plus W3y. That's going to equal, okay, this ends up equaling because the equal to resultant times the y bar. Okay, so we found moment about the x in order to find y bar is the center of gravity. This is going to be what's called x bar, y bar, z bar. Sorry, just for notation, x, y, and z are the center of gravity, center of mass for our system. Okay, so the total of the three individual moments about the x-axis has to equal the total moment replaced about all three. Okay, so I don't actually care that I found this by taking moment about x. What I care is this piece, okay? That the weight of particle 1 times its y position plus the weight of particle 2 times its y position times the weight of particle 3 times its y position equals the weight of the resultant times the resultant of the center of mass. Okay? We can take moment about the other two axes and get identical equations about x and z. So we have W1 x1 plus W2 x2 plus W3 x3 equals the resultant force times x bar. Okay, and then we have the same thing in W1 z1 plus W2 z2 plus W3 z3 is equal to WR times z. Okay, so solving these will allow us to find the center of mass for each particle. Okay, so essentially what we've done is done a summation of the weight times its position, weight times position plus weight times position equals this. So I'm going to rewrite these in general. That this reduces to x bar equals summation of xw over summation of weights. Okay, so the summation of each particle's weight times its x position divided by the summation of weights. Okay, this is the exact same equation I had just up here in terms of the x's. I've just rearranged it a little bit. Summation of weights was what we called WR a moment ago. Okay, XW is X1 W1, X2 W2, X3 W3, and we'll similarly have the same thing for Y bar. Summation of Y W over summation W, and Z bar equals summation of Z W over the total weight there. Okay, this is important. This works for a system of particles. Okay, it gets a little bit more complicated when we have continuous surfaces, but it's good to start to see how this works in terms of symbol of particles in order to get the sense of how we can use moment in order to replace total force with three individual forces with one combined force applied at the center of gravity. So moving forward, looking at a solid object as opposed to particles. And again, we're going to find center of gravity. Okay, so now we're going to deal with this random blob-shaped rigid body. Okay, and we're going to make this closed. Okay, so it is a solid object in three-dimensional space. We want to replace this with a single force, point force, that represents its weight, and we need to know we need to know where to apply that. Okay, we said for a system of particles, okay, we said x bar was equal to summation of x w over summation of w. Okay, and this is for a system of particles. a system of particles. But this solid object we can treat as a system of particles. Millions and millions and millions of tiny little particles that make up this object. Okay, each one of those little particles, and I'll just pick one little rectangular particle here. One particle here is going to have some sort of differential volume, some tiny little volume amount that it has there, and it is going to have some tiny amount of weight, okay, dW. So our total volume is made up of all these tiny little volume elements, and our total weight is made up of this. Okay, so what we can do here is take all of these little particles and add them together. So x bar becomes the integral of xw over the integral, xdw over integral of dw. Okay, so the x position of each of these tiny little weights divided by the summation of all those tiny little weights. Okay, and we integrate, and this is from the left edge, the front edge in this case, x1, to the last place, x2. Okay, this integral becomes very, very difficult to solve because of finding out these dw's for each step along the way. Okay, this is our equation for center of gravity. We also have y bar is equal to the integral of y dw over the integral of dw, and z bar equals the integral of z dw over the integral of dw. Okay, and this is for center of gravity. Okay, but there's some interesting things we can do here, well, some simple things we can do here to make this a little easier to work with. Okay, one is, in general, this weight, okay, is going, in general, weight is simply going to be equal to mass times gravity, right? Well, mass, we don't want to deal with mass, we want volume, so weight is going to equal density times volume times gravity, okay? Density is going to be in metric units, kilograms per meter cubed. Volume is going to be in meter cubed, so that's going to be kilograms times meters per second squared. That's going to be newtons for weight. So this is an expression of weight. Okay, if we want to make this a differential, we can see dW is equal to rho g dV. So now we've got a relationship between this tiny little differential weight and a differential value for volume. Okay, so I'm going to use this, and I'm going to take these things, and I'm going to simplify it a bit. I'm going to take my diagram down. This is no longer limited to center of gravity. Okay, I'm going to turn these things into something a little bit more useful. Okay, so center of gravity. Okay, x bar is equal to the integral of x dw, which is now rho g dV, over the integral of rho g dV. Okay, well, I'll just leave that for x for now. I'm going to have center of mass. All right. Center of mass means we don't care about gravitation. So center of mass is simply going to be x bar is the integral of x times density times volume. Again, density times volume is mass. So, and then we have the integral of rho dV. Okay, so it's x times the mass of our little differential element divided by the total mass of all our differential elements. And then we have centroid. Okay, here we don't care about mass or volume, we're just talking about size, geometric space. So we have x bar is equal to the integral of x dV over the integral of dV. Now these are generally fairly easy to evaluate. And I'll talk about how to do that in terms of our shapes and integrating over volume. Again, it's a volume integral, which some of you have seen and some of you have not. But I'll take you through the basic cases on those. And these also work the same for y and z. I'm not going to bother writing those out, but y bar is integral of y rho g dv over integral of rho g dv. X bar, so y bar is y rho dv over integral rho dv. And the same thing for z, same thing for centroid. It extends out to all three. Okay, and this also can show you how these relate in terms of those equalities I talked about. If we're talking about center of gravity and gravitation's the same, then we can pull gravity out of the integral and cancel it. And we're left with this expression. If we have this expression and density is the same, we can pull it out of the integral. Density is constant, we can pull it out of the integral, cancel it, and we're left with the integral for centroid. Okay? If density changes from different spaces in this in the object, we can't pull it out of the integral because it does change with where we are in our volume. So it has to stay inside the integral. We can't reduce it to this equation. But depending on what we're looking for, these are our cases here. There are also things we can do here with 2D centroid. Okay, when we're dealing with something with uniform depth, okay, which we're talking about a two-dimensional object, we'll have x bar equals the integral of x dA over the integral of dA. And for one-dimensional centroid, this is for the example like wires and things like that we can consider thin objects. Wires and rods and things of that nature. We can talk about this, and this becomes the integral of, x bar is the integral of x dl over the integral of the length of the object. Okay, and a 1D centroid does not necessarily have to be in a straight line. One-dimensional just means a thin object. So if I had a cord or rod, a sort of hemispherical hoop here, this would count as a one-dimensional object. Again, it's thin enough that we don't care, and it's got uniform depth. Again, so these are the equations we're going to be working with. I've only left them in terms of x, but they're exactly the same for y and z. You just substitute in your y for x in any case where that applies. Okay. We will be doing primarily with centroids. When we talk about center of mass and center of gravity, it's going to be cases where the density or gravity are going to remain the same. So that we're really just finding centroid, even though they may be asking for center of mass, center of gravity. Just know if you ask for center of mass and it's uniform density, you can just find centroid. If you ask for center of gravity and you have uniform density and uniform gravitational field, then you can just find centroid. So essentially what we're doing in this course is finding centroid. Even when they ask us for something else, it's going to be a case where centroid is equal to those. You just have to be able to spot that that's true and work from there. So we'll take a simple example here of one that we could probably already do. Just to kind of take you through the process and show how this works and some of the difficulties that come out of it. So we'll take a rectangular solid here that has a base of 6 meters and a height of 9 meters. Okay, and this is my rectangular solid. Okay, now this will be my x-axis and y-axis, not surprisingly. This is a two-dimensional problem, so we are going to be working with a two-dimensional centroid equation. Okay, finding the centroid of this, most of you could already tell me, well, center for a triangle, because it's right triangle. We did this when we talked about distributed loads. The centroid here should be at 2 and then 2, 3. That's where the centroid should be, but for this case, we're going to go ahead and do sort of the long way here to make an example of it and show that we can do this. So I'm going to erase this squiggle on the inside. And I'll show you what we do here. Okay. So what we do is we split this into a bunch of differential elements. Each one that is the length or width. It's either the height or the width of the triangle. You can either do it like this, or an identical method of solution. I could use vertical slices. Okay, either way, we have these tiny little elements. This is dA, but we'll also notice that it's, in this case, equal to x dy. Over here, this element is dA, which is equal to okay. So what it comes down to is whether you find it easier to integrate over the y-axis, dy, or integrate over the x-axis, dx. In some problems, it's easier to do one or the other, and allow you to decide which one makes more sense. Okay, but what I'm going to do here is I'll go through this one, and then I'll show that this gives us the same answer either way. Okay, so what we need to do is find an expression for the center of each of these little elements. Center of this little element here is going to be right in the middle, and it's at position x over 2 and position y. Okay? And we also need this expression for the right-hand edge of this. This becomes important here. So we end up finding the equation of this line here. I'll show you why we need this in a moment. This line ends up being, okay, the slope, rise over run, is going to be negative 9.6, negative 1.5, times 6 minus x. Okay, so this is y equals, and if you want to multiply that through, we can go y equals 1.5 minus 9 plus 1.5x. Check your values here. At x equals 0, we get positive 9. At x equals 6, we get 0. That looks good. And that is a line going through those 2 points. Easy enough. All right. So y equals 9 minus 1.5x. This is also y equals 9 minus 1.5x. Okay, so what we need to do here is set up our equation for our centroid. Sorry, technical difficulties there. So picking up where we left off, I'm integrating the, again, numerator. I have the integral for the numerator, integral for the denominator. I will look at the numerator alone here. So that's the integral from 0 to 9. Distributing the y through is minus 2/3 y squared plus 6y dy. Well, that ends up equaling minus 2/9 y cubed plus 6 halves y squared, integrated from 0 to 9. That ends up equaling 2/9 y cubed, 81 minus 1 is equal to 2. 81 times 3 is 243. Okay, so the numerator ends up equaling just 81. The denominator, evaluating that, we have the integral from 0 to 9. Actually, skip that step. I'm just going to go right to minus 2/6 y squared plus 6y integrated from 0 to 9. 81 times 2 sixes is minus 27, plus 6 plus 54 is equal to 27. So the denominator is simply equal to 27. This gives us that the y centroid is at 81 over 27, or 3, right, where we expected it to be. Okay, so that got us one of our variables. The next thing we're going to look at is doing the same thing for x. All right. So the y centroid is at 3 inches. The x centroid, it's the same process. It's a little bit tedious, but you do got to kind of get the hang of this. So now we're going to look at the integral, integrating over x, so 0 to 6 of, this is an important distinction here, okay? This first term here is the position of the length of the moment arm, or the length from, or the, in this case, the x position of the centroid of our little differential element. So it's not just x, it's actually x over 2, okay? Because we're summing up the moments about all this, about the range from 0 to x. So it's going to be x over 2, okay? When we plug in that first term, it's going to be the appropriate coordinate for the centroid for our differential element. It's not going to be necessarily just the raw variable. So 0 to 6 of our x coordinate of our centroid times dA over the integral 0 to 6 dA. Okay, well, we substitute in here. We have 0 to 6 x squared, x over 2. dA is simply x dy. And then this equal over integral 0 to 6 of x dy. All right? So this turns into a big mess. Okay? We can't integrate x with respect to y here or here. What we need to do is substitute in again. So this will end up looking really ugly. 0 to 6. X squared over 2 is minus 2/3 y plus 6 squared over 2 dy over the integral from 0 to 6 of minus 2/3 y, y plus 6 dy. Now this is certainly something you can evaluate. You can FOIL this out, divide it all by 2, integrate over y. This you can integrate again, 0 to 6x dy. We just did this one, we know it comes out 27. But again, notice the denominator is the same in both cases as the one we just solved for when we did the y direction. But the key here, this gets ugly. You can certainly do this and you will get the correct answer. However, this is when this other shape comes in. Okay, this will make our lives a little easier. Rather than solving this messy integral, we can solve one that's a bit easier. If, for this case, we use the vertical slices. So now we're still going to have x bar equals the integral. Now we're looking at the x coordinate here. So it's just x dA over, and this is integral 0 to 6, integral 0 to 6 of dA. All right, here we're left with, well, dA is now y dx. Okay, notice when we change, a lot of our variables flip around. Okay, now we have a centroid that looks a little different. Our dA is a little different. Okay, you have to pick either one full set or the other full set, but it doesn't matter which one you choose. Whichever one looks easier to you, and they will both always work. Some of them lead to rather messy expressions like the one we just saw. Others will end up being fairly straightforward. So this one looks like it won't be quite as bad as the last one. So this is the integral 0 to 6 of x dA is y dx over the integral 0 to 6 of y dx. We do have one substitution here. We have to plug in the y, plug in for y. So this equals the integral 0 to 6 of x times 9 minus 1.5x dx, and the integral 0 to 6 of 9 minus 1.5x dx. Okay, evaluating top and bottom here, I will do this a little bit more quickly. So the denominator is the integral of 0 to 6, 9x minus 1.5 x squared dx is equal to 4.5 x squared minus 0.5 x cubed. That's integrated from 0 to 6. 36 times 4.5 is 162 minus 0.5 times 6 cubed, 216. That's 1/2 is my weight. So this equals 54. Okay, the numerator equals 54. Trying not to lose you off the edge of the board there. The denominator, as you might have guessed by now, again, it's just the integral of dA. We're going to end up with the same 27 for the area we got before, but just to show that that's true, we end up with 9x minus 0.75 x squared integrated from 0 to 6 equals 6 times 9 is 54 minus 6 squared is 36, 3/4 of that is 27 is equal to 27. 54 over 27. 54 over 27 is simply 2. So just like we expected, x bar equals 2 inches. So here we got the same value that we would expect to get given the geometry in the case. However, we did go through some lengthy integration here in order to solve for those values. Okay. Do another example here of one where you'd have to use the integration. Okay, taking a look at this. Very simple parabolic shape. This curve follows the shape y equals x squared. And we're going to say it's 1 meter tall and 1 meter wide. And we're again going to find the centroid. Okay. I'm going to, just because I have y equals x here, I'm going to make vertical slices. So dA, the differential area here is going to be equal to y dx, because it's height y, and width dx. The centroid is right here at x comma y over 2. Okay. And now I'm going to go ahead and evaluate this in terms of the integrals. So I'm going to go x bar is equal to the x position of the centroid is x. Oops, this is integrated from 0 to 1. I'll make this a little neater. 0 to 1 of x times dA over 0 to 1 of dA. dA is y dx, so we have the integral 0 to 1 of x times dA is y dx over the integral 0 to 1 of y dx. We know y equals x squared, so this is 0 to 1 of x cubed dx over 0 to 1 of x dx. Okay, the integral of x cubed is x to the 4th over 4, evaluated from 0 to 1. And this is x squared. Oops, y equals x squared. Sorry, y gets substituted for x squared. So this becomes x cubed, evaluated from over 3, evaluated from 0 to 1. This ends up 1/4 divided by 1/3, which means our center of mass here, x bar, is equal to 3/4, which makes sense. The x position of our center of mass is about 3/4 of the way over, somewhere in this vicinity, somewhere along this line. So that makes sense. We have x bar is equal to 3/4. And this does show that sometimes these integrals aren't as nasty as they were in the last one. Okay. Oddly enough, the cases when you have to do the integration, oftentimes it ends up easier than the cases that you could have done geometrically. So now we're going to go ahead and solve for y bar. So now we have y bar, the y position of the centroid, is equal to the integral from 0 to 1. Again, now we're integrating over, we're still going to be integrating over x. So we're going to have y, the y position here is simply, the y position for the centroid is y over 2 dA, 0 to 1 of dA. And so then we end up with 0 to 1 y over 2 dA is y dx. Okay. Notice an important detail here. Even though I'm solving for y, I'm still integrating over x. That's important, because if I'm integrating over x, I have to use my x bounds. I go from 0 to 1. Granted, in this case, it's to 1 in both cases. But if I extended this up higher, or if this didn't end at 1, 1, if these dimensions were different, like they were in the last one, okay, your integration bounds have to match the variable you're integrating over. Okay, they don't match. If I'm finding y bar, I don't automatically use my y range. That is a mistake. Your integration boundaries are governed by what you're integrating over. Even though I'm finding y, I'm integrating over x, so I'm using my x range. Same thing here, 0 to 1 of y dx. Okay, again, now I'm still integrating over x, so I need to substitute in for y. So this becomes 0 to 1, y over 2 becomes y squared. Substitute in, this becomes x to the 4th over 2. Okay, x squared over 2 dx. This becomes integral 0 to 1 of x squared dx. Okay, integrating this becomes x to the 5th over 10. Integrating from 0 to 1, this becomes x to the 3rd over 3, 0 to 1. This equals, okay, that's going to be 1/10 divided by x cubed over 3 is 1/3. This is going to be, again, 3/10, 1.3. So our y position of our centroid is, I'm going to change these to decimals just to stay consistent. So this is going to be at 0.75 meters. The y position is going to be at 0.3 meters. Again, that makes sense. So we're going to be 3/4 of the way over, not quite 1/3 of the way up. So right about in here, which does appear to be about the centroid for our object. And this is at 0.75, comma 0.3. So that's finding the centroid of something where we would have to use the integration. Again, we could have done horizontal slices. It would have been a little more difficult. We would have had to flip this around and use x equals the square root of y during our integration. But either way, it will work. Okay. So the next piece is, again, a lot of parallels with distributed loads here, is if we have a more complex shape, called a composite body. Okay, this is a series of connected shapes. Okay, what you can do is find the centroid for each shape, each piece, then use the particle equations. Okay, first thing I mentioned at the beginning of this lecture, we said the x bar for what we were talking about, center of gravity, was the summation of xw over the summation of w. Well, this is center of gravity, center of mass. It's the same sort of thing. We have x bar equals the summation of x times the mass of each particle times the summation of masses, or centroid. We have x bar is equal to summation of x times the volume over the summation of volume. And 2D, that would be area. 3D, 1D, that would be the length. All right, so it works the same in each case. So we find the centroid or find the center of mass, center of gravity, and then using each of those pieces, we plug them into the particle equations and are able to combine them. And the particle equations are essentially just a weighted average, which you'll see when we get through the first example. So we'll take a chance to see a couple of different things here, and we'll take a look at a three-dimensional piece here, a three-dimensional, oops, shoot that over here, I guess. X, Y, and Z. Okay, so I'm going to make we're going to have a wire here, kind of a hoop shape in the x direction, then it extends over in the y, and then down in the z. So we've got a wire bent into sort of an odd shape here. In terms of dimensions, this distance is going to be 20 millimeters. This distance is going to be 40 millimeters. And I'm going to give you the radius of this circle. Oops, let's draw it from the center. This is a hemisphere. This is a half a circular hoop. Radius is going to be 60 millimeters. Okay? So that gives us our dimensions, and locate the centroid of the wire. Again, as it's bent into this weird shape. Okay, picking up again. We're middle of example here. I've got this wire. It's got a hemispherical hoop here, plus some extension out in the y direction, extension down in the z. Finding the centroid of this, we're going to split it into 3 sections. Okay, and obviously one of those is going to be the little hoop. Then we have the horizontal piece along the y direction, and the vertical piece in the z. The other thing we need to know about each, we need to know where the centroid is. Okay, and we need to know the length of each piece. Because if you think back to what the particle equation is for a one-dimensional object, for a centroid, it's that the x position and the corresponding y and z position are equal to the summation of x, again the x centroid, times the length of each section, or in this case each particle, in this case each section, divided by the summation of the total length of the wire. Okay, so the centroid here, the center of a hemispherical hoop, okay, is, well, in this case, the x centroid is at 30 millimeters. The y centroid, it doesn't extend at all in the y direction, so it's 0. The z direction, okay, this is something, it's a fairly irregular shape, but a lot of the standard, more common irregular shapes, hoops, hemispheres, trapezoids, things like that, there's actually a table on the back cover of your textbook that will tell you where the centroid is for a hemispherical hoop. Looking at that table, you get the y centroid, the z centroid sticking up here is at 2r over pi. In general, in this case, 2r over pi is going to be 120 over pi for that. Okay, the length of that piece we have, okay, half of a hemisphere, that's pi d would be the entire hemisphere, 2 pi r. So we just have pi r is 60 pi. And 60 pi will be the length. Centroid for this straight section here extending in the y direction, that's going to be 0 in the x. In the y direction we have 20, in the z direction 0. Its length is 40. The vertical piece here, the centroid, okay, x direction doesn't extend at all in the x direction, so that's 0. The y direction, again, its entirety out here at 40. And its z direction centroid is at -10. Its length is 20. Okay, so what we do from here is we go ahead, well, first of all, I'm going to turn these into decimals. 120 divided by pi. Okay, 38.2. 60 pi is 188.5. This is in millimeters. These are also in millimeters. Okay, so now we can go ahead and solve for, I'm going to take this down so just for board space, but I'm going to solve for the x, y, and z centroid here. So the x centroid, it's going to be the summation of x times L for each one. So we have 30 times 188.5 plus 0 times 40 plus 0 times 20 over the entire length. Well, this is something that's useful to know in its entirety. 188 plus 40 plus 6 plus 20 is 248.5. So that gives me an x centroid of 30 times 188. Divided by 248.5 is 22.75. 22.76. Okay, so the x centroid here is 22 centimeters out in the x. The y centroid is equal to 0 times 188 plus 20 times 40 plus 40 times 20, all divided again by the total length is 248.5. So the y center mass here, y centroid, is 800 plus 1600 divided by 248.5 is 6.44. Okay, so the y center of gravity, center mass, is only 6.44 out here, and I'm going to make some space here. So our centroid is at 22.76, comma 6.44, and then the z is the last piece. We have 38.2 times 188.5 plus 0 times 40 plus negative 10 times 20. all over again to 48.5. Okay, adding this up, 38.2 times 188.5 minus 20. So 7180.7. Okay, notice we do keep this negative sign here. This is going to shift the center, the centroid down into the negative z direction, so we do want to be subtracting that out. Because again, if it's balanced between top and bottom in the z direction, we want the positive additions from the top, the negative additions from the bottom to cancel out, so the centroid can end up being at 0. Okay, this ends up equaling 28.90. And that's in millimeters. So 22.76, 6.44, and 28.9 in the z. So that's where our center of mass for this wire is. Okay, and you can find those just again looking at the individual pieces and then adding up those pieces as a weighted average with their length. Okay, so looking at a composite piece here, one other strategy we can take a look at here, and that's the idea of looking at negative area or negative volume. And that'll make a little bit more sense as we look at our sample here. So take a look at my XY coordinate system here. Say I've got a triangular piece over here, and then I'm going to go to this. Okay, I'm going to change that a little bit, make it a little bit more scale. Okay, and it's not really to scale, but we'll pretend. All right, so we're going to say this is 2 feet. This is 1 foot. This distance is 1 foot. This distance is 1 foot. This distance is 3 feet. Okay, so we have this shape here, and again, find the centroid. And we'll make it easy. Call it the shaded area with the shaded area being this chunk. All right. Now, this is mostly just an exercise. You could easily find the centroid for the triangle, find the centroid for this rectangle, and then find the centroid for this rectangle and add them all up. But to show you how negative area works, what I'm going to do is I'm going to have an imaginary triangle, rectangle right here that I'm going to use. So what I'm going to do now is I'm going to take the triangle and this big rectangle minus this little rectangle in the middle. Okay. So I'm going to have 3 sections. The triangle has a centroid and an area. And again, dealing with 2-dimensional centroid, we have, for each one, we have the summation of x times a over summation of a. So now instead of length, we're dealing with area because we are dealing in 2 dimensions. So for our triangle here, the centroid for the triangle, again, this is my origin here. So triangle, it's going to be 1/3 of the way over here, so my centroid in the x direction is going to be 1. Centroid in the y direction, 1/3 of the way up is going to be at 1. Area 1/2 base times height, 1/2 times 3 times 3 is 4.5 square feet. And I'm just going to label these. There. Okay? The big rectangle centroid for this piece is at -1, 1.5. Okay, just looking at this big rectangle here. Area there goes over 2, up 3, the area is 6. Okay. And then what we look at here, we have this little rectangle here. Its area, red rectangle, okay, its area, its center of mass, centroid, is going to be at negative 1.5. Its height is it going to be at 2. The centroid is going to be at 2. And its area is 2 by 1. But keep in mind, we're talking about negative area. So this is going to have an area of negative 2. Okay, so when we plug in our weighted values, that's going to sort that out. So our total area is going to be 10.5 minus 2, 8.5 square feet. And I can do my weighted averages the same way I did before to get my centroid. So x centroid is going to be 1 times 4.5. Just combine these are going to be pretty straightforward. 1 times 4.5 is 4.5, plus negative 1 times 6 is negative 6, plus negative 1.5 times negative 2, okay? Removing area from the negative axis does shift it positive, so it's going to be a positive addition to our x position on our centroid. So negative 1.5 times negative 2 is a positive 3. This all over the total area of 8.5. So the x position here is 1.5 over 8.5, which I don't want to do in my head, is 0.176. Okay, same thing looking at y. Y bar, center of mass, and this is in feet. Okay, so there's this x bar is actually going to be in the positive side of things, so we do have a little bit more there, but this is 0.176. We'll look at y. Again, this should definitely be positive. There should be no negative contributions here. So y, we have 1 times 4.5 is 4.5, plus 1.5 times 6 is 9. 2 times negative 2 is minus 4, all over 8.5. Y bar is equal to 9.5 over 8.5, which is 1.12 or so. .12. This is in feet. This is in feet. So y bar is 1.12 feet. So our center of mass here is at 0.1, 1.12, right about in here somewhere. Again, if the drawing were to scale, this would give us the answer there. So so that wraps up this in terms of how to approach the finding center of gravity of a composite object. Again, you can find the pieces of each individually, either doing it geometrically, or you can include the integration on these pieces to get there. You can find your center of gravity by adding up each section, treating each section as a particle of the given area, length, or size. Okay, so there was some confusion about some of the notation in the centroid equations. I'll start looking at an example here. If I take a look at a curve here, area under a curve, say I take this curve and I'll make this y equals 2x squared. Okay, and I'll take that from 0 to x equals 1. Okay, if I'm looking at the area under that curve, we'd always take a look at, we'd start by slicing it into differential elements. I'll start by looking at it in vertical elements. Okay, and I would use x and y, and the rest of the lecture I used x and y to talk about points along the curve, but then when I also plugged into the equation for centroid, we have x prime equals the integral of x, whoops, I'll put that in there in a second, of x dA over the integral of dA. Okay, in this case I used this x as different from this x. It caused a lot of confusion, I think. So I'm going to switch to what the book uses for notation. Okay, x and y is the point on the curve. the point at the center of our differential element, they call x tilde y tilde. And what gets plugged in here is the x tilde, and then for the y equation, it's y tilde dA. Tilde just being the squiggle on top of the letter. Okay, so we have these two here, and we can define x tilde and y tilde in terms of x and y. Okay, in this case, x tilde, well, it has the same x coordinate as the point on our curve, so that's just going to be x. Y tilde, well, that's half of the y value. Again, it's halfway between 0 and the point on the curve. So y tilde is just going to be y over 2. Since we know y is equal to 2x squared, we can just simply make this 2x squared over 2. We can drop the 2. So y tilde just ends up being x squared. Okay, this allows us to solve this pretty easily. Okay, I'll start with the x term here. So the x term, x prime is equal to the integral. Well, we need to know the area of our differential element here too. Its width is dx, its height is just y. So dA is going to be y dx. And again, y is equal to 2x squared. So dA is equal to 2x squared dx. So we can substitute in here. X tilde is x. dA is 2x squared dx. And we're integrating from over x, so we go from 0 to 1. Denominator is going to look very similar. 0 to 1, we don't have the x tilde term, we just have 2x squared dx. Solve this out. The numerator ends up being 1/2. The denominator ends up being 2/3. This evaluates out to 1/2 divided by 2/3 is 0.75. Okay, so our x-coordinate of our centroid is at 0.75. Okay, that makes some sense. We can evaluate the y term as well. Y prime is simply equal to the integral of y tilde dA, which in this case equals y tilde, we said, was x squared. Integral of x squared times dA is 2x squared dx. And again, we're integrating over x. Doesn't matter that we're solving for our y centroid. We're integrating over x, so we go from 0 to 1. Denominator is the same, 0 to 1, 2x squared dx. Oops, y prime. Numerator here is 0 to 1 of x squared times 2x squared there, times x squared times 2x squared dx. This ends up equaling 2/5. Divided by the denominator is going to be 2/3 again. This ends up equaling 3/5 or 0.6. Okay, so our centroid is going to be at 0.75, 0.6. Okay, and if you look at this curve, you find this point here, plug in 1 squared, this is going to be 1, 2. So it makes sense that our curve is at 0.75, 0.6 is going to be right in here somewhere, which is about the centroid of the object. Okay, this is using vertical rectangles. I'll set it up doing horizontal rectangles. Okay, horizontal rectangles ends up being a lot more mathematically intensive, but I'll set it up at least to show you how this would work. And again, a big skill in these problems is being able to decide which direction, which set of rectangles you want to make. Generally, you want to have one of them butting up against one of the axes, but I'll show how this works in a second. So if I get rid of basically everything in here in green, this is still true. So I still have my curve. I still go from 0 to 1. This point is still 1, 2. Okay, now I'm going to make horizontal rectangles. This point on the curve is still x, y. The point in the center is still x tilde, y tilde. That's going to be quite a bit trickier to find in this case. Area is also going to be trickier. Okay, well, I'll do the area first. So dA is equal to, well, the height's easy. The height's just dy. The width here, well, x is at this point, so the width is simply going to be 1 minus x. Okay, so 1 minus x is this width, x is this width here. X is this distance, so this is 1 minus x to get that. So it's 1 minus x times dy. X tilde is quite difficult here, actually. Well, not difficult, but it makes it difficult when you try and end up integrating it. Okay, that's the coordinate of this point. Okay, well, if this is x, this is 1 minus x. So we're going to make this x plus 1 minus x over 2. Okay, that's a messy expression, but we'll deal with it here. Okay, x is this distance plus half of the width of this piece. So we have this plus this is the coordinate of x tilde. Y tilde is easy. Y tilde is simply just y. Okay, so that becomes our x tilde and y tilde. Now, when we integrate here, when we plug in here, we're going to have x prime equals the integral. X tilde is x plus 1 minus x over 2 times dA is 1 minus x times dy. This is all over the integral of 1 minus x dy. Now what makes this especially awful is we have to integrate over y, which means we need to substitute in for all these x's. We know y is equal to 2x squared, which means x is equal to y to the 1/2 over radical 2. Okay, just rearranging, solving that for x. Bring the 2 over, take the square root of both sides. Okay, so in for all these x terms, we have to substitute y to the 1/2 over radical 2. Then we integrate our integration bounds. We're integrating over y, so we go from 0 to 2, 0 to 2. Doing this out, after all the substitution, we will get the same answer we got doing it the other way. We will find that the x-coordinate is 3/4. We do the same thing with y. Okay, now again we're looking at the integral of y tilde dA over the integral of dA. Y tilde is simply just y. dA is 1 minus x dy. This integrates from 0 to 2. This is also 0 to 2 of 1 minus x dy. Okay, so again, integrating that, we should get the same 0.6 we got before. All right, we're substituting in and going through. So the point here is to distinguish x, y with no notation that's along the curve, x tilde, y tilde, which is the centroid of each differential rectangle, and then we use those to solve for x prime and y prime, which are a centroid of the entire shape.